Well, good morning, everybody. So I'm talking about this subject because I have been helping a number of people. So from maybe 2 or 3 decades ago, when I first started making my own cycle-accurate, timing-accurate 1130 replica, I was diving into this strange world of 50s and 60s mainframe technology. And then I was lucky enough to buy an 1130 and restore it. You can see it in the upper left. It's the yellow machine. And that got me pretty experienced with it. Then I started volunteering at Computer History Museum out in Silicon Valley and restoring the 1401 and other systems and got to really like restoring those. And I began to help out different people, so museums in the UK, Endicott, Baltimore, and so on, who had 1130s who were restoring them or had problems with them. And what I began to notice was that I was working with these brilliant people. I mean, they were very talented, educated engineers, experienced digital designers. They had restored tons of equipment. They could walk up to a PDP-1 with a blindfold on and shoot problems. But they were struggling sometimes to figure out what was going on with the 1130. And I spent a lot of time translating, trying to explain how to think about this with analogies. And so that was really the formation of this presentation, is to try to give you a start if you're going to do this. So imagine you walk up to this 1950s, 1960s IBM system, and you open the documentation, you're getting ready to do a restoration. And, at first everything seems fine, and then things are getting off a little bit. Seems a little strange. You're entering the twilight zone. You're in a parallel universe because this machine was developed by aliens. It was developed by aliens because they created computers, and it's very similar to the way we did it, but lots of choices are different. There are things that are subtly different, things that are wildly different. And so it takes quite a while to make that jump from their universe to yours. And that's what I'm going to try to help here with. So one of the first things that you realize is that it looks like English, but they use language in a very different way. I'm just going to give you a couple of examples here because I guess like an archaeologist who has to learn Linear B or Aramaic to study what they're studying, with IBM you have to understand what they mean and how they say things. So this is a circuit breaker, right? Interrupts power if there's a overload. Not the IBM. A circuit breaker is a micro switch activated by a cam lobe. So you'll see circuit breaker, wait a minute, I don't see a circuit breaker here at all. Or current switch logic. Any of you work with current switch logic? Actually, a lot of you have because it's ECL, emitter couple logic. But because IBM invented it, that was the name they used in the original patent, and they just continued to use that, ignoring what the rest of the industry did, what academia did. So they'll continue to call this current switch, and you have to know how to translate it. Even weirder, what's an AC trigger? What's a kind of a logic gate? We would know this as an edge triggered gate, but to IBM, it's an AC triggered gate. So all of this terminology that's kind of odd that you have to translate to something to deal with. And it goes on. There's a lot of mechanical things with bails and interposers that they talk about in the documentation. And then odd things like dotted or and dotted ands that we'll look into. So it's solid logic technology is the basis of the 60s machines, starting with 360 and the 1130. But it's not too different from the prior generation, SMS, which was used with the 1400 and 7094 generation. But even here, the terminology gets a little different. So here we have a fiberglass board with traces on it and components. So you consider that's a board, right? Nope, not the IBM. That's a card. The board is what we would call the backplane on the right. So little thing, not as confusing as AC trigger, but you have to first figure out their terminology to be able to follow the documentation. Now those boards go into gates. Every board is a compartment with the card stuffed into it. It's not just terminology though. There are design practices, things they do that are maddening in dealing with them. And this is pretty consistent through all their products for many decades. And one of them is their documentation. In some ways, they have wonderful documentation, lots of details. And I can tell you, as long as it's matching the particular version of the machine that you're working on, it's correct. It's just useless. It's useless because they do these things to save 5 minutes of drawing time. So rather, if you imagine engineers working on a circuit and they have to add a gate, and there's not room to put it on that page, what would you do? You would redraw the page with the gate in place. Now what they do is they have a connector off the page, then they rifle through every other page till they find a little space somewhere, stick the gate in, and then route it back. So after a while, you're chasing things, page after page, where there are gates that have nothing to do with what else is on that page, but it saves somebody having to redraw a diagram. Or you might find a schematic where everything flows from the plus rail upwards to ground. So it's not incorrect, it's just unusual. So you have to flip it in your brain to think about how it's working. Ken Sheriff, who was just mentioned in the prior talk, worked with me at Computer History Museum restoring the 1401, and he was working on the card reader, the 1402, trying to trace some signal. And he saw the signal go off page, jumped to the next page, went through that. Page after page after page, it kept routing through the page and then off again. And when it got to the end, it was connected to ground. And when you went to the first page, it was like 1/4 of an inch from that first signal was a ground. So here was a case where obviously at some point there had been a micro switch or something, and then they got rid of it. The engineer didn't want to waste the time erasing the line. So they did that. So you can waste a lot of time because of the documentation, but it is accurate. This is not really a synchronous machine like you're used to because they don't have any clock flip-flops. So states are just set and reset. Things aren't really happening on a clock edge with a master clock distributed like you think of in any modern system. And that has a lot of repercussions in how you deal with the machine. So those flip-flops are just set by some pulse that comes in. And that pulse might be triggered by something external to the machine that's not even synchronized to the CPU clock at all. It's whenever a disk sector mark happens to come up, pulse comes in, flip-flop changes. IBM loves inverted logic. So you'll find most signals are something like minus stop. And so if minus stop is true, then it's running, because it's not stopped. So you have to get your head around that as you look through all of these things, combining signals that are not minus stop and minus sector mark and so on. Their gates are not nice, standardized, well-behaved gates like we have the privilege of dealing with more modern technology. And I'll give you a couple of really interesting examples as we go a little further through here. Now, the logic in both the SMS generation and SLT generation is diode transistor logic. So that just means the logic function's implemented with diodes, and then a transistor inverts it and amplifies it to redrive the signal. And that's pretty much what you find except for some of the current switch, the ECL. A lot of voltages. So in SLT, IBM has multiple families of different speeds, slow, medium, and fast. They all have their own logic 1 and 0 levels, their own voltage rails. And then to make it even worse, IBM has chosen to leverage, good business sense, older technology that they've designed inside the new one. So when you look at a 360, some of the cards in there are SMS from the 1950s. The power supplies are all leveraged things they built in the 1950s. Why redesign them? So you've got this oddity of power supplies that have to support equipment from the 1401 and equipment from tabulating equipment, pre-computer. And every one of those introduces another power rail. Now, even within the basic gate, there is each individual gate doesn't have just one rail like TTL, +5. It has +6, +3, and -3. So 3 rails just for an AND gate or an OR gate. So you're going to be dealing with a lot of power supplies when you deal with these. Now, IBM would leverage older equipment. So if they had a 1403 printer from an older generation and you want to offer that with an 1130 or a 360 system, you don't want to have to redesign the controller for it with modern SLT. So you take all the cards from an older 1400 and hide them in a box called a 2821. And so you're just physically putting SMS cards as like a hybrid next to SLT cards. And that means you need all of the power supplies for SMS as well. So the basic gate, and this is really their Swiss Army knife logic gate, is the AND OR invert. So the logic function is the diodes on the left. So if any of all those diodes are high, have high inputs, then the junction of the diodes is high, and that means there's voltage triggering the transistor to conduct. So the transistor is pulling the output to ground. Now, if any of the inputs goes low, it's going to pull the junction down, and the transistor cuts off, and now the pull-up resistor on the right pulls it up to high. There's some additional things in here where you can extend it to have more inputs. So if you want to go from a 3-input AND to an 8-input AND, you just add more diodes to the extend pin, for example. So very handy little device. So when IBM draws their logic diagrams, their automated logic diagrams or ALDs, they use a little square box. They don't use a symbol for an AND or OR gate like we're used to. They've ignored what the rest of the world did. And so this is what you're going to find. It's a square box. The left side are the inputs. The right side's the output. Notice that little triangle there, right angle. That means the output's inverted. So in IBM East, the way you read this is you take the inputs, apply an AND. If they're all true, the output's true, so you emit a 0 because it's an inverted output. And if you look at the truth table, you realize this is a NAND gate. Why don't they just call it a NAND gate? Well, they don't care. Here's another one, the OR gate. You see this a lot in SLT as well. Now you notice that the inputs are inverted and the output's not. So if any of the inputs is low, then it's true and you get a 1 on the output. Exact same truth table. It's a NAND again. So 2 NANDs, they have 2 different ways of drawing a NAND gate, none of which look like anything you're used to. So still not too bad. Once you figure out the translation, you know how to deal with this. Then they combine them. I don't know whether this was to save on space and ink or why they do this, but this basically means if you look at the conditions on the left side, top and bottom, if any of those are true, the AND of the inputs, then the OR is true and you get a inverted output. We would draw it like this. Makes a lot more sense to see it like this. So when you're approaching this machine, you've got to translate all the time these into modern symbols that you used to. Now, what about the dotted OR, the dotted AND? Why in the world would you waste valuable transistors and diodes combining signals when you could just twist the wires together? So they just wire together multiple outputs of gates, and they call that a dotted OR. So in some ways, it's just like open collectors in a common bus where any of the gates will pull it down. So it produces an inverted output. So it does save transistors and things, but it makes it a little harder to figure out which of these gates is pulling the output down because they're all electrically combined together. There's no isolation. Now, they use dotted OR and sometimes they use dotted AND. And I finally figured out the difference is if the output signal is named inverted, minus stop, then it's a dotted OR. But if you name it plus go, then it's a dotted AND. So a lot of these things are drawn kind of to the way the designer happened to think about the circuit, not any standard practice. So I have a flip-flop. That seems pretty straightforward, right? Only thing slightly different is the flip-flop has inverted set and reset, but it's a lot like an SR flip-flop. So we should understand this, and to a large extent you do. So if you send a negative pulse on the set line, the flip-flop changes. Now you have Q, the positive output, plus an inverted output. So what happens if you send a second set pulse and it's already set? Well, on a well-behaved gate, it would just remain set. Not an IBM flip-flop. You get a glitch out of the diagonally opposite output. Or if it's reset, and you do another reset, you get a glitch out of the Q output. So there's a lot of gates in here to protect from this. So you'll see that they're looping the outputs back to block signals so you don't set it twice or reset it twice. You think someone would have just redesigned the flip-flop, right? Now this AC triggered gate I mentioned. Very, very handy. So this is an AND gate, and you have 3 inputs. You see the diagonal, the inverted ones. But that N there, what's that mean? That means it's edge triggered. So you could call it falling edge and rising edge, like the rest of the world does. But no, this is negative going edge, N, or P for positive going edge. So you see a letter there, and it means this gate will produce a pulse on the output if it sees this falling edge, but only if the other inputs are active. Think of them as arming. So the other ones arm the gate to be sensitive to the edge, and then if it sees the edge, it emits the pulse. So give you an example of why this would be handy. You have a disk drive and you're writing to it, and you want to know if while you're writing you hit a sector mark. Well, that means you've overrun, you've got an error. Well, you just write is one of the arming signals, and the sector mark is what's the edge trigger. If it edge triggers, pulse goes out, turns on an error flip-flop, you've detected the error. Now, what you notice from here is that IBM does not have to synchronize external inputs. There's no concept of cross-clock domain in dealing with this, because whenever the pulse happens, this flips. Doesn't matter if the main CPU clock is in the middle, right at a clock edge, or not. So a lot of things are happening kind of asynchronously, which is good, but it's also bad if you're trying to catch this on a logic analyzer and you're looking at using the clock as the sampling point. You might miss something that happened just a fraction after the clock. So the truth table is just this. If all the arming inputs are on, then you get a blip. Next gate you'll see a lot is a single shot. This is kind of the 555 timer of the IBM world. So if any input goes low, you emit a fixed timed output pulse. So pretty handy for dealing with peripheral devices. This could be microseconds to milliseconds. They're adjustable. Now here's one of my favorites. Took me a while to wrap my head around this. This is how they implement a latch. They don't use a flip-flop because that's expensive, too many transistors and diodes. And back in this day, every diode and transistor cost money to IBM. So they really worked hard to cut it back. So as we saw before, both of those gates are NANDs, but they chose to draw them 2 different ways, as an OR and an AND, just to logically think about the fact the first one is setting and the second one is resetting signals. So if you send a set pulse, it flips the output, not latch, is now 0. So not latched is 0, so it is latched. Again, everything inverted. Then from a reset standpoint, if you send a negative pulse on the reset, it flips not latched to true, so it's not latched. It reset it. So you'll see these all over the place, and you just have to logically realize that's what it is, a set of conditions that set it and a set of conditions that reset it. I was working with a couple of people restoring an 1130, and they had a logic analyzer on, and they saw something weird. So they saw 2 NOT gates, 2 inverters in a row, 0 in, at the far end is 0, that's right, but the middle wasn't +3. It should have been, right? SLT, 3 is a 1, a logic high, 0 is a logic low. So they put the scope on it and saw it was, fractional voltage. And thought, well, maybe we've got a short or some problem. But that wasn't true in this case. It was working perfectly fine. That's because, again, to reinforce, these are not standardized, well-behaved gates. It's all analog underneath. What you have to learn in dealing with this is be ready to go analog beneath the digital abstraction, because the way things behave are, really violate what you think is happening at the digital gate level. So here's one of those standard diode transistor logic gates with an input down at 0. So it's got it to ground. So that means that the junctions pull down, the transistor's cut off. That pull-up resistor on the top right is delivering +3 volts out. That's what we expected to see, wasn't it? And if it had been a normal gate on the other side, the second inverter, that would have been what we would see, because the diode would have nicely isolated things. But to save on the cost of the diodes, IBM wired the second gate just directly to the transistor, no diode. So the +3 volts is actually flowing down through the last transistor, pulling that down to 0.9 volts. So that's why you see this anomalous looking result. It's because you have to look at the actual implementation sometimes to figure out what's going on. So just very quickly on this slide, the point is that an open input or a high input, all the same. The only thing that counts to DTL is if you're pulling current down through the diode to pull that junction down to 0. That's all that counts, is taking it down to ground. Everything else by default is a logic 1, which means that you'll see a broken trace will look like a perfectly happy logic high state. Another one that frustrated somebody else is they saw a push button coming into the computer. Now, a number of you, if you do design work, you know what a metastable state is with gates. So if you send signals into our normal modern clock system, sometimes it won't quite go to 0 or 1, and it takes a few cycles, which is why you'll see a chain of flip-flops to introduce an external signal in so you can get it synchronized to the clock. Otherwise, this wacky thing happens. Luckily, it doesn't have to happen with IBM because they're not a clock system. But their push buttons, they use +12 volts. They decided that gives them more margin for corrosion and resistance on the contacts, still get a good signal. So here's +12 volts, goes through a little resistor, through a debouncer, and into a SLT gate. So first thing you think about is the gate is 3 for high and 0 for low. Why are you sending 12 volts into it? That would not make a TTL gate happy. Perfectly fine, by the way, with SLT. But what they were seeing when they put something on that input was when they weren't pushing the button, it was -3 volts. Wait a minute, that's an open contact. Where's -3 coming from? And when they pushed it, they saw only +4, not +12. Because it's all in the details of how the debouncer is implemented. It's a resistor capacitor network pulled to -3, one of their voltage rails. So if you don't push the button, it's at -3. And because there's a resistor in both, there's a voltage divider. So the value going into the gate is 4. That's between +12 and -3. So you have to do this to understand some of what you see, to debug what's normal and what's not. And to realize that these gates are enormously resilient, because -3 is just fine to send as a logic level 0. Anything that'll pull that through that diode current down to turn on the next one as a 0 is fine. So -3 is as good as 0. +12 is as good as 3. The only limit is, for the plus side, what voltage is so high the capacitor, the diode breaks down. So there'd be a real high one, but impractically high. And the only limit for -1 is how much current you pull through it. So now power supplies. I mentioned there being lots of rails here. So we've seen with just this medium speed SLT logic that they use +6, +3, and -3. So that's 3 separate power supplies you've got to get working right just to power this particular type. IBM's power supplies were designed in the 1950s for their 1400 and 7000 series. And they didn't see any reason to change for the SLT generation through the 1960s. So no power MOSFETs back then. These are linear supplies, no switching supplies. What they used was germanium transistors, because that's what they had in the 1950s. So you get an IBM mainframe from 1968, and it's using germanium transistors with a regulator burning a lot of energy to get that voltage regulated. Now, if you don't need the voltage to be very precise, almost exactly 3 volts, then they would use ferroresonant transformers. So that looks like a regular power transformer, but it's bigger, heavier, and more expensive. And it has a capacitor across it that causes the iron core to be saturated. So it's in resonance and the core is saturated. And the value of that is if the building electricity goes up or down, doesn't change what's coming out of the other end, because the transformer core is already saturated, so it can't add any more oomph if the voltage goes up. So nice way to get a mostly regulated, say 48 volts for a solenoid. So you'll see a lot of those ferroresonant transformers in this generation. Now they protected their logic. They protected it by having, of course, the regulators for that purpose. And also having overvoltage protection. So there's a crowbar circuit in each of these regulators. If the voltage gets above some trigger, it's going to short out the regulator and cause its fuse or circuit breaker to pop so that you don't burn out the logic chips in the machine. These are all SMS cards, by the way, the 1950s generation, as are the regulators. Then they have sequencing logic. And because there's all of these different voltages involved, there's a sort of a delicate sequence that you have to get power up in the machine. So it will step the power on and validate that the rails are there at each level. The 1130 that I work on is pretty simple. Once it sees +6, +3, and -3, then it turns on everything else. But there are some machines where there's quite a number of steps in the sequencing up, and if any one fails, the machine doesn't power up all the way. So you have to be able to debug the sequencing logic to get these things clean. Then the voltages to support older technology. So the usage meter on an IBM machine that shows how many CPU hours? They borrowed that from their punch card pre-computer. So it needs its own voltage level. There's only about 5 parts in the power supply, but heaven forbid they should waste a minute engineering a new version. So they just have a power supply just for the usage meter in every machine, an extra one to worry about. Now, the other thing to be real careful here is each of these regulators is fed from its own transformer secondary, so they're floating. And that means they can do weird things with them relative to ground. And if you're not careful, you can short out test equipment or blow a fuse if you sort of naively connect across 2 of them. So here are the power supplies in a relatively simple IBM 1130. Look at all of those DC and AC voltages that you need. So the first thing you have to do with any machine, obviously, is make sure the power is good, right, before you deliver it to the logic. And you spend more time on one of these systems because you want all of this to be rock solid. They're core memory-based machines. That was the technology for memory in the 50s and 60s. And core memory has this sort of interesting promise for us. It says, I'd be happy to tell you what's in me, but only if you erase me. So the only way to find out is to erase it and then see what was in it before. And so if you don't want that to go away, you better rewrite it. So every core memory machine has a cycle of read and write, read and write. That's all you ever do. You can't just do a read or can't just do a write. So if you're writing a new value to memory, it's going to read and ignore and then write in the second half of the cycle. And that shapes the design of the entire machine. So when you look at an IBM 1130, it's multiple memory access cycles. You fetch instruction, fetch an index register, do the execute. And the last thing that you'll notice in here is because that's kind of the core of the machine's design, if you ever have to introduce some value, say from an I/O device, or you want to jam in a branch instruction to an interrupt handler, they will just jam it into the memory output register, meanwhile telling memory, don't really read and write. So you see everything organized around the memory. So interesting challenges in doing a restoration, besides that weird set of ways that they look at things and do things. First one, of course, is the private labeling of parts. So those transistors that IBM buys, made by TI, made by Motorola. It even has the logo of the maker on it, but its part number is 108 or 26 or 86. So big challenge if you want to replace a broken part because you have to figure out what it really was. So you might use a transistor curve tracer or something else to figure out how to replace it. For some reason, their part shop isn't open anymore. Really wish it was. So you will end up cannibalizing things, finding old spares, or reworking something to a different type of part, or even having to create something from scratch. Now, the nice thing is, at this level of technology, it's easy, because the SLT and the SMS before it, discrete transistors, discrete diodes, resistors, capacitors, you can look at every signal. You can replace it. If you wanted to make a replacement for one of those little modules that's on a card, with modern surface mount transistors and diodes, you can fit all of those on a little circuit board the exact same size. So very easy to design and make whatever you need to replace it. So that is one advantage. Because these signals are kind of asynchronous, not changing on a clock, your data capture, you have to be a little more smart about how you capture data, what you trigger on to know what's happening. IBM provides some very helpful examples in the documentation. They'll show you what all the signals on an oscilloscope would look like during, say, a disk read. But they do one thing that's subtle that will trip you up if you don't realize it. If one of the signals is inverted, and most of them are, the IBM FE would flip the scope from plus to minus polarity so that it went up in the logical order. So if it's minus stop, they would flip it so it really would go up instead of down. So if you're looking at your scope, not altering the polarity based on what IBM names the signal, your traces are not going to look like theirs. Their mechanical stuff, in some ways, is marvelous, but they've avoided having to do electronics, microcontrollers, or even state machines by using gears and switches and other linkages. So just the Selectric typewriter that's on the top of the 1130 is about 3,000 parts in that thing. So nightmare of complexity. And you'll find this throughout card readers, throughout all sorts of things. Now, they've also leveraged it a lot, so the keyboard is really an 029 key punch. If you know an 029 key punch, that's the keyboard in a 360 console. The 360 console typewriter is a Selectric, IO Selectric. Then whoever selected the oils, the greases, the foams, and the rubbers for IBM's 1960s products made some very bad choices. Very bad choices. The oil and the grease will collect dust and turn into cement. So if you have an old Selectric in the closet and you haven't run it a while, and you turn that typewriter on, it's going to be frozen solid. The foam that they use for soundproofing turns to dust, or it turns to tar, or it turns to both. So you have patches of goop and patches of dust. Got to scrape all of that junk out of there. The plasticizers and the plastic parts have all evaporated by now. So they're now brittle. So something that was just perfectly fine before is going to snap. So most electrics, there's a pulley to hold the cord tension. That snaps because the plastic got too brittle. So we have to fight all of that. You have to, Ryan had to tear out all of the old foam and put in new foam in his 1130 just to deal with that. Now, one thing that's very helpful with this glue that they call oil and grease is something called Nyclock oil. So Mark Verdeel turned me on to this when I was working on something years ago. And it's a clock oil that's so light and thin that ordinary clock oil feels heavy by comparison. And what that means is if you squirt some of that on a cemented solid joint, it just slides in between the old lubricant and the metal. And then you turn it a few times, and it's moving. So it's just a brilliant way. You just have to be patient enough to find these 700 or 800 moving parts and lubricate each one. But it works. And then the last thing I want to leave you with is don't be deterred from this because there are a lot of upsides. Documentation is good. Now, I like 50s and 60s computers because later in the 70s, IBM realized that they were competitors making compatible versions of everything they sold. And they started hiding the documentation. So in later machines, you can't get this kind of detailed logic diagrams, schematics, and whatever. So it makes life harder. Because of the low integration level, it's really easy to debug these. Just you have to think analog. Easy to make substitute parts, like I mentioned before, and it's pretty resilient. So you can extend one of these machines because of this concept of the dotted OR. That is, if you see some signal that says not interrupt request, you stick an open collector modern chip on it to pull that down to 0, and you've triggered an interrupt. And you don't have to add a different gate with more inputs to it because they're just using this dotted OR. So it's brilliant in some ways for being able to add functionality to these systems. And the component quality is pretty excellent. I mean, in all the years I've been working on these systems, I've never seen one of the large filter capacitors be bad. I mean, they're on spec, low ESR, at capacity. I've seen a couple of smaller ones be bad. There's tantalum capacitors on every SLT card for the power rails. So, we all shudder when we hear tantalum. I've only heard of one of them causing a problem, and it was in a machine where they had seriously misadjusted the power supply, so they delivered way too high a voltage to the card. So it maybe gets a pass. And I've seen a couple of electrolytics where the capacity was still fine, but the resistance was getting a little high. So very great products. The resistors are almost spot on their value, 50, 60 years later. So one of the advantages of them is they really picked high quality parts. So with that, thank you very much. I'd be glad to take questions. Thank you. Thank you.
Thank you very much, Carl.
I've left up a picture of the VCF machine, just for fondness. Any questions? Right there. This about cycle accurate?
Now, I was just curious, as you're going through these old diagrams and making sense of them, have you been transcribing them to modern format?
I have done that. It's laborious to do, but a couple of times in dealing with, I won't say which museum, but a particular museum, trying to explain how it worked and them trying to figure out this craziness of single shots giving pulses and during that AC trigger gates going. So I tried to redraw it in a way that made sense. And it took a fair number of hours to get that all done, but I thought it made it a lot clearer. Sometimes I have to do that for myself because between all the negatives and the strange gate symbols, if I don't redraw it, I can't figure out what is it this is looking for until I see what the conditions are.
Thank you.
Okay. We have someone up front here?
Where?
Bob, yeah.
Can you speculate why IBM was so much more successful given seemingly over-engineered and under
Well,
innovative?
there are a number of reasons. So one of the things that you only realize about IBM when you really study them deeply is that the core of IBM was a sales organization selling high margin items with an extremely intense customer connection. And it didn't matter what the product was. And that's why you've seen IBM go into typewriters, out of typewriters, printers, not printers. Really doesn't matter. The company is a sales company, a great one that, when they got the Watson over from NCR, a great sales company that knew how to deal with customers and smother them and do what they needed to keep the customer happy, how to invent FUD and block competitors, whatever they needed to do. And that's really the success more than the technology. Now, sometimes they failed if they got too far behind. Like in scientific computing, they were too far behind CDC, and they were not successful during that interval because no amount of schmoozing and jet travel and tickets to the Super Bowl is going to make up for the computer being half the speed.
Next.
Jeff.
So the phone company had divestiture, the breakup of the phone company. IBM had consent decrees that the government said you're a monopoly. And so they negotiated settlements, some of which was open standards. So can you comment on how they did that, because Memorex and others made accessories for the 1130. If it was so hard, how did they do it?
Well, see, 1130 was easy because that's when IBM had all the documentation available. What makes the restoration so easy for us. So someone like Memorex could just look at the documentation. National Semiconductor could look at the 158 ALDs and recreate them in modern TTL gate for gate because it was all there. So that allowed the competitors. Now with the consent decrees, IBM did start providing documentation, but like all IBM documentation, 100% accurate, not so useful. So they would make OEM guides that would talk about certain things. They'd all be correct, but you had to do a lot more thinking than what was written down to really understand it. So it was sort of like comply, but.
Thank you. In one of your slides, you showed a flip-flop that was set and reset and clock. Could you consider that to be a JK flip-flop?
Well, because it's not clocked, so I sort of consider it an SR, really, because of its behavior. Plus, if both went at the same time, it would toggle. So it's kind of like JK, but I mean, it's really, I think of it more as SR, but it's its own animal.
Because JK had the advantage of zero hold time as well, which was quite useful.
Right. Except I bet JK won't give you a glitch on the other output, will it?
Yeah. And one other thing, you're talking about metastable conditions. One advantage that Schottky logic had, that only Schottky, not low power or fast, is if the inputs changed at the same time as the clock, both Q and Q bar outputs would go low, and you could detect that and then use that to condition your...
Right, with some more safety logic around it.
Was any of that sort of thinking in the IBM?
They didn't need it because, remember, they were never taking signals in and matching them to a clock edge because it's not a clock synchronous machine. I mean, there's a clock, but that's sort of a reference point. It's like here's something that says it's time 3 and it's during the plus phase, but that's not when signals are changing right at that edge. It's just something that's combined combinatorially to decide when something might happen. Instead, everything happens with that AC triggered one when the pulse actually happens. So if you push that button, it doesn't matter if it's near the clock edge, on the clock edge, or way off of it, it's going to flip the AC gate. So there's no need to synchronize, no need to worry about metastable conditions because you don't have this problem of when the clock age happens and when the input changes.
Okay, thank you very much.
Right.
Here you go. Hey, thanks. So I have a question about the power supplies. So you mentioned it was the ferro, what was it again?
Ferro-resonant.
The ferro resonant, yeah, okay. So you were describing how you basically saturate it, right? So that if the input voltage goes above a certain threshold, it won't pass through, right? It will keep it to a certain level,
Yeah.
right? But if it's lower, it won't pull it up to the right level, right?
Well, see, you
will.
saturate it below the target level. So
Yeah.
basically, there's a relatively wide range above and below. So if it's set for 230, for example, 30 volts, it might be saturated down at 200 or 190. So there's really no change in that entire range above 190. So for the reasonable swing of the building, there's very little change on the output. It's not perfect, but it's pretty well regulated.
Okay, and that's, I mean, and I'm not, I haven't studied electrical engineering, but it sounds kind of like an inductor, but I mean.
Yeah, so you'll basically see a capacitor connected across a primary winding. So there's a main primary, then you see another winding with just a capacitor across it. That's your cue that it's a ferroresonant. And so what's happening is that capacitor and the value of the winding is tuned to 60 hertz. And so when 60 hertz comes in, that thing is feeding back like crazy and saturates the core. That's the magic of it, they tell me.
I have more of a comment. You can tell that this machine was made by mostly mechanical engineers,
Yes.
considering how asynchronous it is.
Yeah, if you think about it, IBM had been building like rifles during the 1940s and a lot of scales and time clocks and other things. And you sure see that some of the really experienced engineers love a mechanical device, don't like that newfangled. And by the way, if IBM draws a transistor in a schematic, it does not look like a transistor anyone else draws. It's just like 3 boxes stacked up with an arrow to show if it's, PNP or NPN. So they persist in avoiding or ignoring what the rest of the industry and academia does and do it their own way.
Okay, just a real quick, short question. The ferroresonant transformers are also known as constant voltage transformers.
Mm-hmm.
They were pretty popular in the 50s and 60s. So, and question, with all the mechanical problems, which I know a lot of those challenges, have you seen people doing 3D printing of replacement parts for them?
Sure. Yeah, and I haven't yet seen people do 3D printing with like metal, really high-end printing process, but with plastics, sure.
The gears and stuff.
In fact, yeah, if you look at the machine that the System Source machine has on exhibit here, if you look at the back cover, there's some 3D printed latches because the cover was missing, and so I engineered something that would work and just printed off some parts.
To add on to this fellow's earlier comment regarding the clear mechanical engineering going into the electronics on the IBM 1130, I've been doing typewriter repair some 10, 11 years or so, and all I'll say is I've been avoiding any IBM products like the plague with regards to repair, because they do everything different. They do mechanical spaghetti coding.
Yes.
You have components here that were designed by one team of engineers, that you have mechanical push rods going all the way across.
Absolutely.
Do something made by a completely different team of engineers.
Absolutely. If you've ever looked inside a 1442 card reader, there's these long, long rods doing that, exactly what you say. It looks like Rube Goldberg has designed the machine. But they work. They were very talented engineers.
Here we go.
Some-
Boy, I'm getting my workout today.
Apparently, a former IBM person here wants to make a comment.
All right, we're good. Thanks. First, I wanted to thank you for the work you do and for working on our computer, because that's what got me started in my whole career.
Me too.
In middle school, I had the privilege of working with an 1130, and it's like changed my life. So I can't wait to see this thing run.
Yeah. That was my first hands-on computer, too.
Then, can you tell me what SMS and SLT stand for?
Oh, SMS is Standard Modular System, and SLT is Solid Logic Technology. So at the time, integrated circuits were coming out, but IBM said at the volume we build things, they're not ready. We can't do it to quality. But we're going to have to deal with the competitive pressure of not having ICs. So let's hide the transistors in a can and call it solid logic technology, so it's almost like it's an integrated circuit.
Because I think DEC used their modules with transistors and diodes, et cetera,
Right.
early on because the 7400 series was too expensive, I guess. So
Well, it's expense and also the volume they had to try to get the yields up and everything. So they figured out, they did a lot of early transistor work and then turned that over to TI. A lot of TI's transistor technology was given to them by IBM. So they figured out how to get yields and do things in the early days of transistors.
thank you.
Anybody else?
So of this era, what do you think is the best documented processor out there?
I think they're all well documented. I mean, as long as you have the ALDs. The problem that I think we face a lot in restorers is because the ALDs are marked restricted or not, for use. When somebody has them, they either throw them out or they don't keep them with the machine. Or if there's a museum and they have the ALDs, they still feel like if they might annoy IBM if they show a schematic from 60 years ago. So they'll kind of hide them in the collection and you can't get your hands on them. But I think that were really well documented. It just,
Okay, maybe I should phrase that a little differently. So after this, I'm going to go and Google, some documentation.
Sure.
What would you recommend I start with?
But just get on bit savers. I look at the smaller end systems, so 36030, 36020.
Okay.
1401's a little more challenging. So 1401, IBM decided that logic gates would come in two flavors, two genders. So there's an and another and, because they had two different logic voltage ranges, -6 to +6 or 0 to 12. And they would alternate. So one of these type gates would feed the next one. They never normalized the voltage, so you had to have the right sequence of these gates. So now you've got even more rails. So it's a little more complicated figuring it out, but they're still pretty clear systems.
Okay, thanks.
Here you go.
Just a comment, which is thank you so much
Oh, you're welcome.
for your Rescue 1130 blog. I've been a foreigner to the IBM nomenclature, and you just every day you come out with more clarification, explanation. Anybody who has any interest in understanding how IBMs work, go to Rescue 1130. Carl's blog is amazing. Also, to the other people in the room, if there are people who understand the FPGA tool chains, go and help Carl, because he has been struggling so much with some of the FPGA
Yeah,
stuff
I have
that
one
he's
of
been
those,
doing with.
Intel chips that's like the combination of ARM processors and trying to get the bootloader to support the multiple buses between the two sides has just been an unnecessary headache. So,
I teach that class.
good. I would love to talk to you about that. I mean, I've read every documentation, followed every recipe, copied every one I have, and just. I've got them all on my laptop. I'd be glad to show you. I kept trying. I don't give up easy. So.
And more of a comment on the documentation side of things. I work at IBM. I work up at IBM Poughkeepsie, and the corporate archives are located there now. And they have always been welcome to, if you email the corporate archives and ask them, hey, do you have a document on X? If they have it, they will scan it for you and send you a copy. If it's something that, like ALDs, they might say confidential, they will go to legal and clear it and make sure that it's okay. And generally, for a lot of the stuff, it is fine.
Good.
It's usually the stuff where it's like, it's still semi-relevant. It's still kind of architecturally relevant. So, I've heard some stuff where some of the bus and tag stuff, it's like technically some of that DNA is still in the channels of mainframes today. But they are very helpful. They don't have a lot of the more technical stuff. I think more of that is available out in the public. But certainly IBM is generally not getting upset, and I've generally not heard of any instances where they've gone after anybody for anything.
It's odd. It's
anything
everyone's
before the
afraid of
90s.
them, but I've never seen them stepping on somebody.
No.
But all the museums are afraid of them.
Because, and generally, like they obviously don't do technical documents for the modern stuff, but, you know, other than software side, but all that's freely available. You know, they just have that available. They've never
Yeah.
really
It's kind of a
charged.
pity because in some ways, you know, with all of the consent decree problems they've had over the decades, the lawyers have advised them that, you know, when you get to a certain point, it's better to get rid of the documents than to have them and have to explain some possible interpretation of something. So a lot of great things have just been trashed at IBM that we would have hoped would have been preserved for history, just, you know, because legal said that's a good idea.
Well, and with working with the archive, sometimes it's not that somebody said we should throw this out and not keep it. It's more that the
No
archives.
room.
Well, no, it's that they just weren't told that it was being thrown out. You know, I find stuff in bins at work all the time, and I take it out of the bin, and I'm like, "Do you want this?" And they're like, "Yes, absolutely," because you know, people just don't think. You know, a lot of people at IBM don't think, "Oh, we have an archives," or that they would care.
Right, yeah, this is old, it's not a modern product or a
right.
current product, who cares?
But if
Thank
you
you.
ever do have a question about that type of stuff, certainly reach out to the archives. They're more than happy to help. You know, obviously they have the capacity. You know, they
But
can't.
clearly, I know you and I have a shared interest in the schematics of some
Yes.
unique cards for the 1130 that they probably don't have, or you would
Correct.
have gotten them, right? So-
Yeah, exactly.
Anybody else?
Now, as to the question from the fellow in front of me who can't see me because you're looking the wrong way, every corporation has a library and a hierarchy of libraries. And so for the learning and a machine, principles of operation is the Bible of how does it work. So because Carl was talking about the electronics, and there's a whole hierarchy of documentation. So perhaps, Carl, you should give a quick about, if you don't know what an 1130 is, where do you start, rather than looking
It's
at
called
flip-flops?
functional characteristics for the 1130 instead of principles of operations for some unknown reason. You know, what's also interesting is everyone loves to think about animating one of those 360 consoles with all the lights, but those lights have nothing to do with the principle of operations and the software. They're mostly internal implementation details of that particular model, and you'll never get them if you implement at the instruction set level. You'd have to get down at the gate level for those lights to make any sense.
Any further questions? I have two questions. One,
Yep.
were there any shared SLT cards between 360 and 1130?
Oh, sure, yeah.
Yeah?
Yeah, absolutely.
And
You'd think there would be more, but IBM seemed to, at the drop of a hat, allow a new unique card to be designed.
And the other question is, so the same principles are going on in the 360,
Right.
where they don't have master clock.
Right.
Oh.
Right. So even in the 370, 158, so some of the plug compatible manufacturers trying to speed up the 158 would find that the arithmetic unit doing like multiplies and stuff was all of these asynchronous pulses, and it was a nightmare of them trying to organize it and get it to operate faster. So yeah, that was a common design practice until they stopped showing schematics, and I don't know what they do now.
Well, thank you very much. If there are any last questions, I get them in now. Okay, thank you very much.
thank you.
Please give it up for Carl Claunch.